Hello, everyone. So hopefully you got my email. Did not realize that we had a professional development day on Tuesday. So we are about a lecture behind, maybe half a lecture behind. So your test is actually getting moved to next Thursday, Friday. All right. So that will give us time. So we don't have to rush today. I mean, I could probably squeeze it all in, but I'd rather not. So that'll give us some time on Tuesday. And then I put it on Thursday, Friday, because we don't traditionally have classes on Friday. So you can have a day that you're not having to like actually sit and lecture to take it. If for some reason anybody cannot take it those days, reach out to me and I can give you guys an override for a different day. But try as best you can to get it done then. There is a notification on Moodle that will indicate that there is a change in the date. So if you forget this and on Sunday you go to take it, it won't let you take it. So you'll see that. So hopefully you got to enjoy a little bit of time off on Tuesday. We had finished up talking about, we were looking at the Rydberg equation and how, here we go, how it applied to the Bohr model, right? Which is this simplified sort of understanding of the behavior of electrons. So thinking the Bohr model is where we think of electrons moving around the nucleus like planets in a solar system. And we were able to sort of work backwards from this equation and figure out these changes in energy around these little solar system paths. And it all worked out, except when you moved past hydrogen. So when we moved past hydrogen, we found that this really simple model, the solar system Bohr model, didn't apply. So we needed to come up with a more advanced model. There was some pieces of information that were good here, though. The one thing being that there are these discrete energy levels. So that is going to pull through in the quantum theory, where we have these energy levels, lowest energy closest to the nucleus, higher energy as you move out and away. And that if you transition from one to the other, that you're going to gain or lose energy. So matter, whether it's really teeny tiny or super large, has a wave nature to it. So we can't explain electrons just under the Bohr model because electrons don't behave in this really specific particle-like way. They actually have wave properties. So here's an equation, and I'm gonna jump between the slides and then we're probably gonna spend a decent amount of time on those notes, the guided notes. So de Broglie came up with this concept that related the wave property or the wavelength. And so your wavelength, which is in meters, let me fill this in a little bit. So this guy is in meters. This is wavelength. Is equal to Planck's constant. So this is Planck. And Planck is, the unit on that is joule times S. Okay, and that's a constant. Divided by M is going to be mass of the object, and that's in kilograms. And V is going to be velocity. That is not talking about frequency. Okay, that's not mu, that's actually V. And this is going to be in meters per second. So we've got wavelength is equal to Planck's constant divided by the mass times the velocity of the object. So an object that's really large, like let's say a human being, is going to have a very big number on the bottom. A big number on the bottom of the fraction bar means that we're going to have a small number in total, or the wavelength is going to be super small. So our bodies do produce a small wavelength disturbance around us, but it is so small, it's pretty much insignificant. But when we have a small mass, that makes the wavelength much more applicable. It can actually, that wave disturbance can actually have an effect on the system. So let's look at two instances using this equation. I'm going to ditch here and I'm going to go over to our guided notes because I like the guided notes for this one. All right, so we've got de Broglie's equation. I'm going to fill that in so we have it over here. All right, we've got our wavelength is going to equal Planck's constant, which is the same Planck's constant as your equations before, times your mass, or I'm rather divided by mass times volume. Okay, so both of those are underneath the fraction bar. So let's look at the wavelength of a dog. So we have a dog that's 50 kilograms, and the dog is riding a skateboard that is going 20 kilometers per hour. I want you to find the wavelength that is coming off of this dog. All right, so your wavelength will need to equal your Planck's constant divided by your mass and your volume. But make sure you're using the correct units for mass and for, sorry, not volume, velocity. I'll give you about 3 minutes to put that one together. Okay, so for this one, we are going to take Planck's constant on the top, which is going to be the same number every time, 6.63 times 10 to the negative 34. And that's going to be in joule seconds. Joule seconds. Mass is going to be in kilograms, and that's good there. So we've got our 50 kilograms. The thing we have to change is this velocity. So this is in kilometers per hour. We need to change that into meters per second. So if we've got, I'll put it down here, if we've got 20 kilometers for every 1 hour, well, if I want to change this into meters, because we're over kilometers, put kilometer down there, that'll cancel there. And then we're going to change our hour. For every 1 hour, we get 60 minutes, not quite far enough. So for every 1 minute, we get 60 seconds. Minutes will cancel, hours will cancel, and we're left with meters per second. All right, or the ending value for this ends up being 5.56 meters per second. So that's what we will plug into the equation here, 5.56 meters per second. Now, when we run this through the calculator, we're going to get a really, really teeny tiny number, 2.39 times 10 to the negative 36 meters. Okay, so a dog on a skateboard is creating a wave propagation, but that wave propagation is on a factor of 10 to the negative 36 meters. So it's compared to the size of the dog, it doesn't really do anything. I want you to run the same calculation, but this time I want you to do it for an electron, okay? So here's the information on the electron. Its mass is 9.11 times 10 to the negative 31 kilograms, and it's moving at a speed of 4.19 times 10 to the 6 meters per second. So you've got both of them, and they are actually in the units that you need, so you really just need to plug it in. So I'll give you 2 minutes in there, mainly just to get practice with getting it into the calculator. Okay, so for this one, we've got our wavelength, again, is equal to our Planck's constant. So 6.63 times 10 to the negative 34 joule seconds, all over we've got our mass, which is 9.11 times 10 to the negative 31 kilograms, super teeny tiny mass. It's moving relatively fast though, 4.19 times 9 times 10 to the 6 meters per second. When we plug this in, we get 1.74 times 10 to the negative 10th meters. Okay, well, that's definitely a bigger number than the previous one. The wavelength is definitely bigger. And an interesting thing is that the diameter of a hydrogen atom is about equal to 1 times 10 to the negative 10th meters. Okay, so this wave behavior of an electron is actually broader or wider than the size of the diameter of a hydrogen atom. So what this is saying is that we actually don't really know where the electron is in the atom itself. So this idea of the solar system, oh, we know the path and we know where the electron is and we know the velocity is, we have to throw it out. In actuality, the electrons are behaving like a wave. They have a probability of where they can exist, and that probability is actually broader than the atom itself. So because of this uncertainty on where the electron is actually living, instead of having orbits, we are going to have these things called orbitals. I know it sounds like almost the same thing, okay? But an orbital is referring to the quantum mechanical model. How is an orbital different than an orbit? An orbital, as opposed to it being like a specific track, like an orbit would be, an orbital is like a probability cloud, or it's an area where we would expect the electron to be, but we don't know exactly where the electron is. So it's not a structure, it's an area or a cloud of probability. So the exact location of our electron, we can't determine. Orbitals, you can say, are an area where an electron is likely, okay? It's likely to be. How likely? Usually about approximately 99% of the time, we've got an idea where the electron is going to be. But there is a 1% chance that that electron is not anywhere near the atom. There's like a very, very small chance that that electron is like on the other side of the universe somewhere, okay? And if this sounds weird and strange and quirky, it is. It's very, very strange, all right? If you want to know more about it, you kind of have to move more into the physics realm. But for now, what we're going to stick with is that there's these orbitals, and they are clouds or areas of probability where we expect the electron to be. Now, when I want to describe an orbital, I need to have 3 quantum numbers involved, okay? There's the principal quantum number, there's the azimuthal quantum number, and then there is our magnetic quantum number. Now, the principal quantum number, or n, is very similar to the n value from the Bohr model. This thing describes the energy level. All right, and we can also think of this as like the distance from the nucleus. So what is happening inside the nucleus is we've got protons and neutrons, so it gives it an overall positive charge. And then around it, we've got this area that we would call n equals 1. The n value is giving us our quantum number. If we move farther out, we're going to get this n equals 2, so on and so on. Okay, 2 has more energy than 1, 3 has more energy than 2. So examples are going to be 1, 2, 3, 4, 5, etc. So we can think of them as energy levels. We can actually stick that down in there. The lower the energy, or the lower the number, the lower the energy level. And you're always going to fill lower to higher. Okay, so I'm going to say fill lower to higher. So I'm going to pack electrons into this first orbital before I start packing electrons into the second orbital. That's all that N tells us. Okay, it's just telling us the energy level. Now, how this starts to differ from the Bohr model, because that may seem very similar to the Bohr model, is now we start to add, yeah, no, the lower the level, the lower the energy. Lower the level, lower the energy. Fill low to high, lower level, lower energy. You can kind of think of that as like floors of a building. So the lowest potential energy that you have is when you're sitting on the first floor. If you take stairs to get up to the second floor, and you had to get out of the building, let's say there was a fire and you were to jump out the second floor, there's a lot more potential energy on your body than if you were to climb out the first floor window. Okay, so energy goes up as we move up in numbers. Now, the azimuthal number, which is denoted by this lowercase l, or sometimes you'll see it because this is typed up, but we'll see it as like a cursive lowercase l. Oh, come on. Okay, like this. This is describing the shape of the orbital. So now it's not enough just to say, I'm at the energy 1, 2, 3. I need to say the shape of the orbital as well. Now the shape is important because it lets us know better idea where the electrons are and how many electrons we could find. So here are some of the shapes and their corresponding numbers. It's just something you want to like either write down or memorize. But we can have L is equal to 0. This is called the S shape. And it's a sphere. And so like this, draw dot back there. So we've got this spherical shape. So if I ever want to describe an orbital that has this shape, I'm going to give it a 0 value in its L position. The next one would be L equals 1. And this is going to be a P shape, or called the P shape. P shape. Or sometimes it's called the P orbital. And we call this, it's like an infinity symbol, or sometimes it's called the dumbbell. It looks like this. Sometimes also called, figure 8. Another shape that we have is if we have L equals 2. This is going to be our D shape. And this is like a 4-leaf clover. And it looks sort of like this. Again, this is not what the electrons look like. This is a 3-dimensional area or cloud where we think the electron may be hanging out. If your L happens to be a 3, you are an F shape. This thing has 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's got 8 lobes around it. This is just one of them. The shapes get a lot more complicated than that, so I'm not going to be expecting you to draw those. Really, sticking with knowing that L is a sphere, or L equals 0 is a sphere, and L equals 1 is this sort of dumbbell shape. That's going to get you through most of it. And this is a 4-leaf clover. Values are integers ranging from 0 to n equals, or n minus 1. So energy level 1. So let's say we have n equals 1. If n equals 1, the only possibility for my L value is going to be 0 to n minus 1. So if n equals 1, I can have 0, and I can also have n minus 1, which would be 0. Okay, so the only thing I can have is the 0, which is the S shape or the sphere. What if I have energy level n equals 2? That means that I can have 0, which is the sphere shape, but I can also have what's n minus 1 or 2 minus 1. That would be my 1 value. I can also have the P or the dumbbell. So energy level 2 actually has 2 different things. You can kind of think, again, like if these are floors of a building, so this is the first floor and this is a second floor, this is a lopsided building, okay? So it's tiny at the bottom and it gets bigger as you move out. So on the first floor, the only classroom shape I can have is a sphere. On the second floor, I can have a sphere shape, and I can also have a figure-8 shaped classroom, all right? So more options on the second floor. If we go to the third floor, we can have 0, we can have the dumbbell, and we can also have the, sorry, let me put, oh, hold on one second. I'm giving you the L values. We can have 0, erase this here. This, I don't want this to say L. I want that to say, no, I just want that one erased. Let's make that a 1 rather than an L. I won't be giving you my drawing tool. Okay, so here we can have in just a second. I don't know what's going on here. You're not going to work for me, are you? Might have to annotate on top of it. Let's try. Why will it not let me draw? There we go. Okay, 1. This one, we can have 0, we can have 1, and then we can also have 2. So in the energy level n equals 3, we have a sphere classroom, we have dumbbell, and we also have the 4-leaf clover. Now, when I get into my n equals 4 energy, right, the 4th floor of the building, the options I have available to me are a sphere, 0, a dumbbell, 1, a 4-leaf clover, 2, and a 8-lobe, or 3. So when you're naming the orbital that you're in, the first number that you're going to give it is going to be the floor that they're on, 1, 2, 3, 4. The second number is going to just tell you the shape. Are you in a sphere? Are you in a dumbbell? Are you in a 4-leaf? Or are you in a 8-lobe? There is one more number, which is the magnetic quantum number, or it's this number denoted by an M with like a little subscript L. Would you ever have a 4th level? Yes, there is an n equals 4. Oh, you're saying over here, would you have an L4? No, we don't have any shapes outside of the F. So the F is the most complicated. What would happen in n equals 5 is we would just start adding more of them to it. So let me just draw it in. So n equals 5 would have the sphere classroom, it would have the dumbbell classroom, it would have the 4-leaf clover classroom, and again, it would have the 8-lobe classroom. There isn't something more complicated that it would have on the floor. So we're getting broader until we get to the 5th, it just sort of stacks on top. Good question though. Okay, so our magnetic quantum number is this M with the little L as its subscript, and this thing is indicating the orientation of the orbital. So this is saying like which direction sort of is it pointing in? So like you can have your floors to your building. So energy 1, 2, 3 are our floors. These L values of 1, 2, 3 are 0, 1, 2, 3 are telling us the shape of the classroom. But we can have, just like you can have 2 lab rooms on the same floor, we could have 2 dumbbells on the same floor that are pointing in a different direction. Maybe one's pointing east and one's pointing west. That number gets indicated by this magnetic quantum number. So how many options do each of these classrooms have? Well, S is a sphere, right? So any way that I rotate that, it's always going to be in the same direction. So this only has one orientation. So 1 at each energy level. And this begins at n equals 1. So my lowest floor has the option to have this circular S shape. Now, if I look at P, the P classroom, or that's the dumbbell classroom, that has 3 options or 3 orientations at each energy level. And this begins at n equals 2. So the first floor, we don't have a P. The P only gets to start at the 2nd floor. Now let's look at a P real quick down here. This is what the P looks like. So when I say that there are 3 orientations, there's one dumbbell that's pointed up and down, there's one dumbbell that's pointed side to side, and there's one dumbbell that's pointed forward and back. So all 3 of these, sort of like you took 3 balloon animals, are twisted around the same thing. All right, so each classroom is identical, but the way that it's pointed or its orientation is slightly different. What about if we have the D-shaped classroom or the D-shaped orbital? D has 5 different orientations at each energy level. In this classroom, the D shape doesn't start until the 3rd floor. So we don't get to have this unique classroom until we get up onto the 3rd floor. The F, which is our final classroom shape, which is sort of our most complicated of the classroom shapes, has a total of 7 different orientations. And this doesn't begin until, you guessed it, n equals 4. Okay, so the top floor, or n equals 4, it's not quite the top, but that is the highest floor where we start to introduce a new sort of classroom style. Now, each orbital, every single orbital can hold 2 electrons. So if S has only one orientation and each orientation holds 2 electrons, this thing can hold a total of 2 electrons. What about the P? It has 3 different orientations. Each orientation can hold 2 electrons, so this holds a total of 6 electrons. D has 5 different orientations for its classrooms, and each classroom holds 2 electrons, so this has a total of 10 electrons. F, 7 different orientations, each holding 2 electrons for a total of 14 electrons. So my S classroom can hold 2 electrons. All of my P classrooms, all 3 of them, can hold 6, my D can hold 10, and then my F can hold 14. I know this seems like really, can seem kind of funky. All these numbers seem random and funky. So let's apply them to some of our orbitals. So let's start with the simplest one. Orientation for the L equals 0. So L equals 0 is talking about a sphere. Okay. Sphere, or the S orbital. So I'm going to draw a sphere here. This is n equals 1. And then if I was to go to my next classroom, it would be n equals 2, followed by n equals 3. Again, these aren't tracks like they were in the Bohr model. This is representing a 3-dimensional sphere, and the electron is somewhere in there. So we can kind of think of these as onion layers being stacked around each other. So the smallest sphere is going to be the N1. We'd fill that first. Once we've filled that, then we'd start to fill the space where the N2 sphere is, and then the N3. So how many orientations do we have at each floor? This is a sphere. How many orientations can a sphere have? Only 1, so 1 at each level. This thing begins at the first energy of n equals 1. And then let's write out one of these quantum numbers to explain it. So let's do this one here. So if I wanted to describe this second sphere onion layer probability cloud to somebody, I would write it like this example. So first I would write my quantum number. What quantum number are we in? We're on the 2nd floor, or 2. So this is your n value. I'm going to put a little comma, and then the next number to come is going to be your L value, which tells you your shape. Well, your shape for this is a sphere, so I'm going to write 0. Okay. So this is your L value. And then the last thing that you're going to do is your magnetic value, or your, what your orientation is. So are you at, like how many different orientations can you possibly have? Now your ML is going to be 0 for all spheres. Orbitals. So this will be 0. This is your ML number. Now, if I was to look at, let's say I was to look at this one instead. that's slightly larger. It would have a numerical value of 3.
Real quick, when you say like if you were to look at the N3, these would be exclusive of one another. Like N2 would not coexist with N3. Like these are just separate things.
No, they actually sort of stack on each other like Russian dolls. So if we were to look at, and it'll make more sense when we start filling our electron configurations, but what I do is I put electrons first in this inner sphere. And then once I've put, let's say we put 2 electrons in there, then I'm going to put 2 electrons in this next sphere, then 2 electrons in this next sphere. So we go from smaller spheres into larger spheres. So if I'm dealing with hydrogen, hydrogen only has 1 electron. The S and the N equals 3 and the N equals 2 don't exist. We only have 1 electron in the N equals 1. But as my atoms get bigger, I have more electrons, so I have to make more shells or more onion layers. Does that make sense? I don't know who asked it.
Yes.
Oh, sorry. Okay. So for this guy here, which is slightly bigger, he would be 3, 0, and 0. Okay, because there's only one orientation. All the ML value is telling you here, ML is what orientation you're in. So in this case, we're in the 0 orientation. It doesn't mean anything really outside of the fact that there's only one possible option for my orientation.
So how are you telling what orientation you're in?
So how do we know what the ML value is?
Mm-hmm.
If it's a sphere, it will always be 0.
Okay.
Okay, so if you're ever doing one of these for a sphere, have your ML value be 0.
Okay.
The way that you solve for your ML value, it's kind of silly, but you take your N value. So you take N minus 1, and then you do a negative, a positive, and 0. So in this case, N minus 1 equals what? 0. Because if we're in, here we're at, or not N minus 1, it's, sorry, I'm messing you up here. For this, just memorize it. That's going to be the easiest thing. So this is just telling us that our only option is the sort of 0 orientation. Let's do the P and see if it makes a little bit more sense, because our ML value is going to change a little bit. So in this case, we have a figure 8. We have 3 orientations. And it begins at level 2. And then for this 3 orientation thing, okay, so what you do is, it's not your M value. Oops, someone's ringing. It's not your N value. You take your L value. So L equals 1 here. So the possible orientations are going to be my L value as a positive, so 1, a 0, and then my L value as a negative 1. 1, 2, 3 orientations. Again, they're not denoted like this one isn't the 0 one, this isn't the negative 1 one, and this isn't the positive 1 one. It's just saying that there are 3 possible options, and I'm giving each of them their own orientation. It's a quick way to figure out how many orientations. So in this case, our L equals 0, or I mean our L equals 1, so it can be 1, 0, or negative 1. Up here, our L equals 0, so the only possible option is 0. Really quickly, just to sort of nail that in, if L equals 2, what are my possible orientations? Are going to be my L value, 2, 1, 0, minus 1, minus 2. So you stretch from the positive value to the negative value, hitting each integer. How many values? 1, 2, 3, 4, 5. There are 5 possible orientations. if we do, let's just do it for L equals 3. This is going to have, as far as our orientations, we're going to do, so we've got 3, 2, 1, 0, -1, -2, -3, or 1, 2, 3, 4, 5, 6, 7 total orientations. Again, these numbers don't specifically mean anything. They're just saying, hey, one of them is pointing in this direction that we're arbitrarily going to call 3. One of them is pointing in a different direction we're going to call 2, so on and so on. So let's go back up here. So we've got our dumbbell shapes. There are 3 orientations. We said that our ML values can be -1, 0, and +1. Now, if I was to do a couple orientations for this, so my energy level, or my N, has to start at 2. I can't have an energy of 1 for the dumbbell. There is no option for this classroom on the first floor. So I have a 2. What is the shape? Well, the shape is a dumbbell. So dumbbell always has the L equals 1. So this is going to be a 1. And then what is my orientation? Well, I have 3 different options. I can be 2, 1, -1. Remember, this is your L value, and then this is your ML value. So this is one orientation. We could say that this is this orientation. All right, I have another option though. I'm still a dumbbell, so I'm still the 2 shape. I'm still an L equals 1, but instead of being in this orientation, let's say I'm in this orientation, which we're going to classify as the 0 orientation. So this guy can be this one. Finally, I've got a 2, a 1, and a +1. So each of these can change. So there are 3 options within each P. We could also do this if we're at, like, say, the 3rd energy. If we're at the 3rd energy level, let's say N is equal to 3. Okay, well then we're at 3, 1, -1. We could have 3, 1, 0. We could have 3, 1, +1. This first number tells you the floor you're on. This second number tells you the shape of the classroom. This third one tells you the orientation of the classroom. Any questions on those numbers before we move into the D?
I'm still confused on how you're figuring out the orientation. Like, why is, so how are you getting +1s and -1s?
That's just the rule of thumb. So you just take your L value and you go from integer positive L to integer negative value.
So it can always have a possible orientation of 0, -1, and +1?
Yes, if you're in the P.
Okay.
Okay, if you're in, so it's, you know, one thing to do is just memorize it. That if you are a sphere, the only possible orientation is a 0. If you're a P, your orientation can be 1, 0, -1. If you're a D, you're going to be 2, 1, 0, -1, -2. One way to figure this out, if you don't want to memorize it, is take your L value. And again, yeah, go from the positive L to the negative L as integers. And this gives me how many values? 1, 2, 3, 4, 5. And there are actually 5 orientations. Okay, why are those the numbers they picked? It just is. It seems kind of silly. It's just the numbers that they picked.
Okay.
Do we need to memorize like which numbers correspond with which orientation?
They don't actually correspond with any orientation. Okay, all they're letting you know is that there's 3 different options. It's just saying there are 3 different orientations. It's not saying this is specifically this orientation. Okay, this -1 could be this. This 0 could be this or whatever. We're just saying there are 3 different ones. So I would never say, I could say, what are the possible options or what's a possible option? But I wouldn't say you need to point out which one is the positive one or which one is the 0, because there's no correlation between those two. It's more of a conceptual thing, just to show you that there are 3 orientations. For this thing here, okay, so D, we know that D gives us this, well, there's clover shapes, and then there's this, you know, some people say it looks like a pacifier or like a dumbbell with a donut around it. And that looks so strange, right? These are actually this is what electrons do. If I was to take a picture of an electron over and over and over again around an atom, it forms these probability shapes. For D, we know that it has a clover shape for most of them. We know that there are 5 orientations. Okay, so we get 5 orientations. And what are those orientations? Well, if L equals 3 for this shape, or I'm sorry, L equals 2 for this shape, then I know my possible orientations will be 2, 1, 0, -1, -2, or 5 different options of pointing that classroom. Where does it begin? It begins on the 3rd floor, n equals 3. So there is no 5 orientation d orbital on the 2nd floor. We only get it on the 3rd floor. So let's do a possible example for one of these. The lowest n that this can be is a 3. So I have to have a 3. What is my shape of my classroom? It's a d orbital, which is represented with L equals 2. So this is my n, this is my L, and then my ML, or my orientation, can be any one of these. So I'm going to just start with this one. I'm going to say 2. What's another possible option for this? 3, 2, we just changed that last number, 1, 3, 2, 0, 3, 2, -1, and 3, 2, -2. Okay, 1, 2, 3, 4, 5 different orientations.
If you were to ask us to give you all the options, do we have to write it out like that, or can we just do
I
it
could
like,
give you something and say, is this a correct orbital for a d orbital? I could say like this, 2, 1, -2.
no?
Is that correct for D? No. There's a couple things it's not correct. It's not correct because D can't be in the 2, right? D has to start at 3. What's another reason it's incorrect? Because your L value isn't 1 for D. Your L value is 2 for D. So something like that. This number is a possibility. Okay. I could also say, we could do something like, so we'll cross that out. You know, is this a correct orbital for S? If I said 4, 1, 0, you would say, no, that's not correct. Why is it not correct? Well, the 4, it can be a 4. This isn't the correct shape, but it can be a 0. So making sure you're matching things on the right floors and in the right classroom shape. So we don't like that one.
What shape would that be? Would that be a 1?
For a sphere?
Oh, it would be a
0. So here is your L value. So what did I put there? Let me scratch it. I had 4, 1, 0. The floor is correct. We can definitely have this on the 4th floor. We can have it on the 5th floor. We can have it on the 6th floor. 1 does not match my L. My L has to be 0 if it's a sphere. When I'm putting a 1 value in, I'm talking about a P-shaped classroom. So this is wrong. That's what makes it wrong. So I would need to make this a 0 in order for that to be correct. The S's are really easy. It's always going to be 0, 0. There's no like option outside of that. It's going to be 1, 2, 3, or 4, 5, or 6, and then it's going to be 0, 0 always.
So I guess I'm not really understanding the N portion of this when it says N begins at 1, or like just right there. How could it be 2, 0, 0?
Because its formation, or it's your ability to use that shape, starts at n equals 1. So the first floor has access to make an n equals 1 classroom. The second floor also has access to make an n equals 1. The third floor has access to make an n equals 1. The first floor has access to make a sphere. The second floor has access to make a sphere. The third floor has access to make a sphere, and so on. So this beginning means like, what floor can I start making this shape? So I can start making the sphere shape at the lowest energy.
Right, but why would one that is like, how could one that is N, that N equals 3 still be spherical, maybe, is my question.
How can this one have a sphere shape? So when you have
Like
Russian,
what happens to the N equals 1 and the N equals
they're still
2
there.
levels?
They're still there.
So is the shape determined by the outermost layer of electrons?
No. So you want to think about this like you're filling your electrons from the center outward. Okay, so this is talking about the different shapes and the ordering that we're going to fill the electrons in. So it's not like I'm describing the atom as a dumbbell. I'm just describing the electron position as a dumbbell, or I'm describing the electron position as a sphere, not the atom as a whole. Okay, so when you have a Russian doll, if you have a Russian doll, that's the third biggest Russian doll. Is it the only Russian doll in your situation? No, you have the second smallest and then the tiniest, because they're all nestled into each other. The same thing is true with P's, but P begins at level 2, meaning that I can't put a P on the first floor, or I don't have a teeny tiny P.
You cut out there. You said P begins, and then it didn't.
P begins at n equals 2. So I can't have a teeny tiny P. I can only have a P that's starting at the second floor. So there's a teeny tiny S, then there's a medium size S, then there's a bigger S. There's only a medium size P, a bigger P, and a bigger P. So we stack on the backs of the previous one.
But does that mean that its inner shell of electrons is a circle and then it goes out to a P?
So it's like, because this is the ordering. I'll tell you over here what the ordering of electron filling is and how we fill them. So first, and that's going to seem kind of wacky, the first thing we fill is the 1s. So I fill the 1s orbital first. Then I fill my 2s. Okay, then I fill my 2p orbital. Then I fill my 3s, then I fill my 3p. Then I fill my 4s, then I fill, this is going to be weird, I fill my 3d, then I fill my 4p back. So first I'm going to fill a circle with 2 electrons. Then I'm going to fill a circle or a sphere that sits around this, and then I'm going to fill a p, which is a dumbbell. Then I'm going to fill a bigger sphere, and then a bigger dumbbell. Then I'm going to fill a really big sphere, then I'm going to fill a 4-leaf clover shape, and then I'm going to fill a dumbbell shape. So they're all sort of nestled into each other around it. So you'll have in the same atom, here is my nucleus. I'm going to fill an S. Then I'm going to fill a bigger S that goes around this. And this is, 3-dimensional. So we've got like a sphere shape here. Okay. Then I end up filling a 2p, which is like this. And that has actually 6 lobes. Then I fill a 3s. Then I fill a 3p, which is like this, but bigger. Then I fill the 4s. So it's very messy. It is a very messy thing. The electrons aren't these neat little paths. The shapes are very strange. It just is what it is. Any questions on that?
When adding in the F on the next level, since it begins at level 4. Wait, what?
This one here?
Oh, since it begins at level 5, F. Wait, no. Wait.
So we're going to get into this a little bit later, this filling thing. And I will actually show you how to read this off of the periodic chart so you don't have to have it memorized, the filling order. Okay, but what's happening is there are different containers. We fill the tiny container before we fill the bigger container, or we close the smaller Russian doll before we stack the bigger Russian dolls over it. Some of the Russian dolls are shaped like spheres. Some of the Russian dolls are shaped like dumbbells. Some of the Russian dolls are shaped like 3-leaf clovers. It's just the way it is. That's just their shape.
So since you stuck the D in between the S and the P, where would the F go in that order?
F, we're not at F yet because F doesn't come around until later.
Okay.
So it's something that is that has the 3D filled. Would it have everything before
underneath
that
it
filled?
Yes.
Okay.
Yes. So we're piggybacking off of the previous atom. So like hydrogen, if you look at your periodic chart, hydrogen only has 1 electron in the smallest orbital, or the s. Hydrogen has 1 electron, so it has 1 in the s orbital. Helium has 2 electrons in that. It's built off of the back of the other one. If I continue on, lithium has the 2 electrons that helium had plus another electron in the s. Beryllium, which is right next to lithium, has what this had and this plus another electron. So we just keep building off the electron before it. Is that making more sense?
That's making a lot more sense. Now,
Okay, good.
could you, just for reference, like maybe take lithium and explain how that would be written with your the three, like the N, L, and M, ML?
So really all we would say is, because this thing is talking about where an electron is. Is it in here? Is it in here? What orientation, what place, what classroom is it in? I'm not telling you the whole layout of the building. This is sort of telling you the whole layout. So if I said, hey, what is this specific electron sitting in? Then we could do it. But do you want me to tell you about this electron or one of these electrons?
So like the outermost, like the
okay, so let's
one
say,
that's in the second.
Yeah, so let's do this electron then. So if we wanted to talk about this specific electron, its N is equal to 2, right? So we'd put a 2 for the first number. Its L value is its shape, which is S, which we give the value of 0. And then how many possible orientations can we have? There's just the 0, right? The 1, which we write as a 0. So the ML value will just be 0 as well. So this electron is in that orientation.
So when we're doing that, we're speaking about a singular electron.
We're talking about a single electron. This is talking about every electron's place, and we haven't really got into that yet, but we will get into it. Probably not until next time.
This makes a lot more sense. Thanks.
Okay, good. I know electrons are so weird. They're so weird. Everybody's always like, why is that the shape? That makes no sense. I'm like, it is what it is. It is what it is. It's because electrons are all negatively charged, so they all want to get as far away from each other as they possibly can. And this is the most efficient way for them to do it. And it does turn out looking like a donut around a dumbbell. The F, you don't need to know the shape, okay? So this is our F1 F shape. It's that weird 8-lobe thing. Don't worry about that, but you do want to know its orientations and a possibility. So if F, we said, starts at n equals 4, right? N equals 4 is where it begins. So the lowest number I could have for my n value would be 4. Its shape is always going to be that L number, which is 3. And then the orientation could be any single one of these. So I don't know, let's pick the -2. I could also do 6 other ones, changing out that last number. What would be an incorrect orientation number would be something like 3, 3, -2, because this is telling me it's the F shape, and F doesn't exist in the 3rd floor. F only exists starting on the 4th floor. Hopefully that makes a little bit more sense. So that's where this is saying the values range from L -1 to L +1. So 7 orientations. Here is sort of a chart that sums up everything that we've just talked about. So we've got, keeps moving too much on me. We've got our N values. So our energy value can be your 1st floor, 2nd floor, 3rd floor, 4th floor. There is a 5th and a 6th floor. Possible shapes on this one. 1st floor, I can only have that 0 shape or the sphere. Possible ML values is whatever my L value was, 0. Here we've got the 2nd floor. I can have either the 0 shape or the 1 shape. Remember, this is a sphere. This is also a sphere. The 1 is just denoting when we're talking about L, 1 is saying that it's the dumbbell. So I can have a 2S or I can have a 2P. If it's 2S, the only ML value I have is going to be 0. But if I have the 1, which is the dumbbell shape, I have 3 orientations for that classroom. 1, 0, -1. 3, we get 3 options, and we start expanding from there. So I'm going to give you a couple, I'll give you a couple of these numbers, and I want you to tell me if it's correct. Yeah, let's do if it's correct. All right, so 5, 0, 0, 3, 1, -1, 3, 0, -2, 3, 3, 0. So tell me if these are possible options. So first look at what floor you're on, then tell me, is that shape okay on that floor? Are we allowed? And then is that orientation making sense? So for this first one, we're on the 5th floor. There is a 5th floor. There's also a 6th floor, 1st, 2nd, and then a 7th floor. So 5th floor, great. What shape are we dealing with? We're dealing with a sphere. Sphere starts at the 1st floor, so every other floor will have a sphere. So that's okay. And then our ML value, so let's put N, L, ML. ML value just needs to fall within the range of positive -L, and it does, 0, 0. So this is good. We like that. This next one, 3rd floor, we have a 1 value, which tells us that it's a P. P starts on the 2nd, so it's definitely available to us on the 3rd. And then this last number just needs to be -1, 0, or +1. So this is good. All right, this next one here, we are on the 3rd floor. We have a sphere shape. Can the sphere shape be on the 3rd floor? Yes, it can. It starts on the 1st and it goes all the way up to 7. Can the sphere have an orientation of -2? No. Too many options there. The only option we have available for us would be a 0. Okay, I'll even do that in red. So this would be a correct option. Down here, we've got 3rd floor. We've got our L equals 3, which is going to be our, we haven't talked about it, but it's going to be our F shape. Well, we talked a little bit about F, but F doesn't start until what floor? F doesn't start until the 4th floor. So this would have to be a minimum of 4. Can this be, this is correct. We could use that. That's a possible orientation, but we are 1 floor too low for that. So silly numbers that seem silly and don't make sense, but what they're telling us is all this is giving us information on the energy, the shape, and the orientation of our orbital. So it's a way for us to describe our orbital. Instead of saying, oh, I'm on the 5th floor and my shape is a dumbbell and it's in the orientation that points in that direction, we can give numbers that tell us the same thing. It is what it is. Okay, so the last thing I want to talk about real quick, you go over again why you can't use the -2. You can't use the -2 here because your orientation has to fall within L to -L. So what is my L value here? It's 0. So the only option is 0. If I wanted to have -2, this value would also need to be 2 in order to give me the option to have it. So if L equals 0, your possible MLs are 0. L equals 1, your possible ML values are 1, 0, -1. If L equals 2, your possible ML values get to be 2, 1, 0, -1, -2. As your shape gets more complicated, you get to have more orientation options. Sphere, super simple, only has one orientation. Okay, well, I guess we will stop there. We'll talk about, there's one more number, an MS number, which is the spin of electron. That one's not too bad. It's either going to be +½ or -½ because the electrons like to spin in the opposite direction of each other. So each orbital holds 2 electrons. One will spin up, one will spin down. So I could add another value here of MS being either +½ or -½ We will re-go over that on Thursday. And then next time we'll talk more about those electron configurations. So the 1s2, 2s2, 2p6, how to read that off the periodic chart so that we can get a full description of it. And then I think your homework was supposed to be due on Sunday. So I'm going to move that as well because I don't want you guys to have to struggle through all that homework if we haven't lectured on it. All right, so you guys are all good to go. I'm going to get all the lectures up today.